So anytime that we're posed with using the Navier-Stokes equations, whether we're trying to solve a problem here in class, or whether we're trying to solve a problem that's an application for something like liquid chromatography or anything like that, we've got to deal with some complicated equations. So what I'm going to do here is we're going to go through the conceptual part of solving one of these problems. And then the mathematics is a totally different story, which we'll cover in the video lectures. But let's look at conceptually how to deal with setting up a problem in Navier-Stokes. So here we have flow in a circular pipe. You can see that here's a side view of the pipe. It's just a normal horizontal pipe with fluid flowing in it. And let's take a second to look at the axes. So the z-axis is going in that direction. So we have flow going down the pipe, just like it always would for a pipe, right? And then we have R. So R is going to be the radial direction. So basically from the center of the pipe out. There's also the theta direction, which is kind of clockwise or counterclockwise around the pipe. So kind of keep those axes in mind as we go through our discussion of how to solve one of these problems. So first thing first, let's start with the equation of continuity. This is kind of a mass balance on everything going in and out of the system, so it's a good place to start. So the first term here, this is density as a function of time, and these are all partial derivatives. So we need to ask ourselves, in this case, is density going to change as a function of time? Well, one of the things that we've talked about, in some of the previous examples, and it holds here too, we're talking about a steady state system. So we're not going to have density change as a function of time. There's no reason for it to. So what we're going to do is we're going to say, OK, density doesn't change as a function of time. That means that term is 0. OK, there's no change in density as a function of time. So you can imagine the numerator of that expression is going to be 0 because there's no change in density. Let's look at the next one. So it looks complicated, and it is a little complicated. But one of the terms I want you to keep an eye on is this VR. That's the velocity in the r direction. Do we have any velocity in the r direction? We actually don't. We just have flow flowing down the pipe. There's not going to be any kind of velocity in the r direction, as long as we're in laminar flow anyway, which is what we have in this case. So this term's going to drop out because that VR term is 0. So that whole term becomes 0 as well. Likewise, look at this term. We've got v theta. That's how fast velocity is going in the theta direction, which again would be clockwise or counterclockwise around the circle. So we don't have any flow in the theta direction either. It's just going down the pipe. This term also can be neglected. So that goes away as well. This leaves us with only this term right here. And the reason why we still have that term is because, well, we said that we have some velocity in the z direction. Does it change as a function of z? Well, if you think about it, in all of these cases, what we really have is this whole expression is equal to 0. Okay, it's a balance. So this whole thing has to equal 0. What we're really finding is that the only thing that we have to worry about is that one term, okay, for the flow in the z direction. But that term turns out to be 0. There's no variance in velocity in the z direction as a function of z. All right, so I've eliminated the marks that we put onto the equation of continuity, but at the same time, we know what we had just done. So we still have that vz term, right, because we got flow in the z direction. So now we're ready to work with the Navier-Stokes equations. So let's take a look at these guys. Whoa, Navier-Stokes equations. I'm just going to get down here away from all of them so that we can talk. So what's going on here are all of the Navier-Stokes equations. But the thing is, we never need to use all 3 of them in my experience. Most of the time, we just need to use one, and then we don't even have to evaluate all the terms that are there in that one equation. So let's talk about these one by one. You see the one at the very top. Look at all those terms. They've all got v sub r in them. We just said that we don't have any velocity in the r direction. So that means that these terms essentially go away. We don't really have to worry about that expression. There's no flow in the r direction. We're just going to ignore it. Likewise, we've got the second one. That goes away too. And the reason why is because we don't have any flow in the theta direction. Really, the only one that we have to worry about is this last guy, which is the one that deals with flow in the z direction. And that's the one that we're going to deal with next. All right, so now that we know the Navier-Stokes equation that we want to use, now we get to neglect terms. So we have to come up with all the terms that we think we can ignore for our analysis. So we're going to go through and we're going to look at each one of these terms one by one. We're going to talk about why we can neglect them. So this first one that we have here, what we're looking at is the velocity of z, velocity in the z direction, as a function of time. So does this change as a function of time? Well, we're at steady state. So no, it doesn't. We can ignore that one. There's nothing that we really need to worry about as far as, well, does the velocity in the z direction change as a function of time? It doesn't. All right, so now we're down to this next term. So we're talking about the velocity in the r direction and then the partial derivative of velocity in the z direction as a function of r. Well, I got to say, the velocity in the z direction is going to change as a function of r because we've got shear stress on the pipe wall, so that's going to slow down the fluid. And we know we're going to have that parabolic velocity profile for laminar flow, so that's one of the things we're going to have to be concerned about. But you'll notice there's this VR term. There's no velocity in the r direction. So we can neglect this entire term, all right? The VR term is the one that does it, but this entire term here goes away. So next, we've got this term and it's got some different velocities as a function of whatever. So what we can look at here is that not only do we not have any velocity in the theta direction, but we also don't have any change in the velocity in the z direction as we go around the pipe. Okay, so if we're at the same r value and we just go around the pipe, doesn't matter, it's not going to make any difference in the velocity of z. That term goes away as well. So you can see that we're able to knock out a lot of these terms right off the bat. Let's look at this next one. So the velocity of z, vz, it certainly, is a non-zero component. But does it change as a function of z? It doesn't. This is a straight pipe. It doesn't change diameter or anything like that. The velocity is going to be the same regardless of whether we're looking at this part of the pipe or this part of the pipe downstream. Velocity is going to be exactly the same. So that term is going to go away too. So now we're on to the other side of the equal sign. What do we have here? Well, this next term is a kind of a complicated looking one. And if you take a look at it, what we're really talking about is how velocity in the z direction changes as a function of r. And we know, again, like I was saying earlier, velocity does indeed change as a function of r, at least as far as we're going in the z direction. So we need to keep that in mind. It's going to be going slower near the wall, and it's going to be going faster in the middle of the pipe. So we can't get rid of that one. This next term, though, velocity of the z direction as a function of theta, this is a second derivative, so how does that curve look like? Well, remember over here we said, well, there's no change in the velocity in the z direction as a function of theta. So if the first derivative is 0, that means the second derivative is 0 too. So that means this term's gone. We can say the same sort of thing over here. There's no change in the velocity in the z direction as a function of z. So the first derivative is 0. The second derivative is 0 too. All right, so now we're down to these last two terms. So the first one is the pressure change as a function of z. Well, remember, we have fluid flowing in a pipe. The reason that the fluid is flowing in the pipe in the first place is it's flowing from a region of higher pressure to a region of lower pressure. That's why the fluid would be flowing in the first place. So we can't get rid of that term. The next one's going to be the change in velocities and all of the different forces due to gravity. But remember, this is a horizontal pipe. We're just flowing in the z direction. We don't have any gravity pulling down that we have to worry about. If the flow was instead oriented up and down, like if the pipe was an up and down pipe, then yeah, gravity is going to pull that fluid down. We have to worry about it. Since it's flowing left and right, we don't really need to worry about it. So that means this term is 0 too. So whenever we start to analyze this sort of thing, all we really have to worry about are these two terms. That's it. And that's what we're going to approach in the next section. All right, so this last part isn't strictly required, but I know I certainly do it every time because I think the Navier-Stokes equations are kind of confusing to use. So once I've narrowed everything down to these last few terms that are left, I always like to go back and look at the physical situation we were talking about to begin with and see, does this analysis make sense based on what we have? So remember the term that we had left over from the Navier-Stokes equations. Now we've kind of extracted it. Let's break it down. There's the product rule that we have to remember from calculus, so make sure that you review that if this looks confusing to you. Once we apply the product rule, we're able to get this expression. So what do we have here? Well, we've got this first term. Okay, so this is the second derivative of velocity in the z direction as a function of r. What it's basically saying is like, well, is there a curve to the velocity in the z direction? That trend is a function of r. We have to remember, if we look at the laminar flow regime, we're going to have this nice parabolic sort of look to the way that the flow is going. It's going to be going faster in the middle of the pipe, and then it's going to be going slower toward the walls where there's a lot of shear stress, and we're going to have this curve in between. So yeah, indeed there is going to be a curve to that profile. So the second derivative of velocity in the z direction as a function of r is indeed going to be non-zero. We're going to have a curve there. Then we look at this next term. Here we have 1 over r, which is non-zero. Of course, our pipe has a radius, so that's going to be a non-zero term. And then we have velocity in the z direction as a function of r. So how does that change? Well, indeed, we do know, just like we were talking about before, velocity in the z direction does change as a function of r. You know, slower at the pipe walls, faster in the middle. So that term is non-zero as well. It should certainly be there. And then the last term that we have is that last one on the right-hand side. That's going to be how pressure changes as a function of z. And as we discussed before, we're certainly going to see pressure changing as we go down the pipe. So it's going to be higher upstream and lower downstream. So based on the physical sort of analysis that we have here, it makes sense with our numerical analysis too for, you know, chopping up all the equations and neglecting terms and everything else. It seems like we've got a pretty good handle on what's going on here. So now we can get to the complicated part mathematically and start to derive expressions for how velocity in the z direction is going to change as a function of r based on what we learned from the Navier-Stokes equations.